We've talked about kinematics, the motion of objects. We talked about dynamics, the forces that cause those motions. Now we're going to talk about objects and their motions in a slightly different way. We're going to start talking about work and energy. Now, energy and work are both colloquial words, right? I don't have the energy to get up this morning, or I'll have to go to work. Well, there are very specific physics definitions for these two words. So energy is a scalar quantity associated with the state or the condition of one or more objects. So an object can have an energy associated with it. Now, there are many different types of energy, and we'll talk about the different types of energy. Thermal energy, how hot is an object. Kinetic energy, the motion of that object. And potential energy, the ability for that object to do work later on, or stored energy. And we'll talk about each of those in detail a little bit later. Energy is important because of a conservation principle that's determined experimentally. Energy cannot be created nor destroyed, but it can transfer from one type of energy to another type. For example, energy of motion. I can start walking. Well, where does that energy come from? Well, it comes from the chemical energy stored in my body, right? I need to burn calories in order to do things. Well, where did that energy come from? Well, plants and animals that I've eaten. Well, where do they get the energy? Well, the animals probably got it from the plants that they ate, and the plants get it from the sunlight. Well, where did the sunlight get its energy from? Well, actually, it's stored energy in the nuclei of the atoms. Mass becomes energy. We'll talk about that next semester. But the energy always exists, it just exists in different forms. So this conservation of energy is an incredibly important principle, and we'll use it to solve problems that would have been too complex to solve through simple dynamics analysis, at least with our level of math. And we can use conservation of energy to get a rough idea of how objects behave. Now, energy can be transferred between different states. One way to transfer that energy is through the concept of work. Work transfers energy to or from an object by a force acting on that object. When you apply a net force, an unbalanced force to an object, you cause that object to accelerate. So that object's motion is changing. You're giving that object energy of motion, which we call kinetic energy. We'll talk about that in a moment. Or you could do negative work on an object. Otherwise you can slow an object down. Imagine a car, you forget to put it in park, your car slowly starts to roll backwards. You quick get out and you push on that car to stop that motion. You remove kinetic energy from an object also through applying a force. And we'll talk about the concept of work and how it associates with forces in the next bit. Now, when examining the concept of work and how work changes the energy of an object, either adds to or takes away energy from an object, transferring it to a different form, we can look at an example where, imagine we have a long, taut wire extending from left to right. And on that wire, we have a little bead, or a little nut. And this wire we're going to pretend is frictionless. So we apply a force. In this case, the force here is downward, some angle theta. And if we apply that force is going to have some component in the x direction and some component in the y direction. Well, the component in the y direction, the downward direction, isn't going to move that nut. That nut can only slide horizontally, right? That's how we set this problem up. So the motion of the nut depends on the x component of the force. That x component of the force will accelerate that nut as it moves to the right through some distance d. F of x, the force in the x direction, is equal to the mass of the nut times the acceleration the nut experiences. Rearranging that simple equation, I can say the acceleration the nut experiences is equal to the x component of the force divided by the mass. Right? Just simple rearrangement of that equation algebraically. Well, if f of x is constant, or if the force is constant, right? We can use our constant acceleration equations, and we're going to assume the force is constant for the arguments put forth here. So if the force is constant, the acceleration has to be constant because the mass of that nut isn't going to change. So we can use our constant acceleration kinematic equations. The one I'm going to focus in on is the speed squared is equal to the initial speed squared plus 2 times the acceleration times the distance traveled. Previously, this might be delta x or delta y. I just have here the displacement as d. Well, here's the acceleration, but I solve for acceleration up here. I'm going to take this term, this f divided by m, and plug it in for acceleration, giving me this second equation. And then I'm going to rearrange this second equation. I'm going to divide both sides. I'm going to subtract v naught from both sides. Then I'm going to divide both sides by 2 and multiply both sides by m. Algebraically, you should be able to follow along with that and do it on your own. But what you end up getting is 1/2 mv squared minus 1/2 mv naught squared is equal to the x component of the force times d. What does that mean? Well, this is 1/2. This is the mass of the object. The mass of the object can't be 0. This is the speed of the object. Here is the initial speed of the object, v naught. Maybe this object is already moving. Final speed of the object, v. Maybe v naught is 0. Maybe the object is stationary, but it doesn't have to be. It's just that note that this force is going to accelerate the object. So the object over here, the bead, should be traveling faster than it was over here. So these terms are related to the motion of the object. If v and v naught are different, that means the object is now traveling faster. That gives this a positive value on the left-hand side. F of x is the force applied. D is the displacement that force is applied through. Well, let's simplify these terms. We talked about how work was the force of the object and how force can be used to do work on an object. So we're going to define that f of x d as work. So the right-hand side of this equation is going to become work. But we want to make it more general than just f of x, right? Because it depends on the force F and the angle theta that force is applied for. If theta is directly down, if it's all in the y direction, then no x component of the force exists, therefore no work can be done. If F is just in the direction to the horizontal, it's just moving to the right, all of it's moving to the right, then theta is 0, and all of the force goes into doing the work. So we have to represent that through algebra. So basically the work is equal to the force applied, this force here, times the displacement that force goes through, times the angle cosine theta, where theta is the angle between the force and the displacement. So displacement, again, is just in one direction. What component of the force is in that direction? If they're parallel, the angle between them is 0, and you just have F times D. So for example, let's imagine my car is stalled on the side of the road, out of gas. You have a friend along, you have a couple of friends along, right? You're driving, you have 3 friends that get out and push. The first person gets behind the car and pushes the car forward. Your smart friend. Well, that motion, the force, is parallel to the direction that the car is traveling. So the angle between the force vector and the car's displacement is 0. Your friend is doing positive work on the car. Okay? Then you have your mean friend, the one that likes to cause trouble, get out of the car, goes to the front of the car and starts pushing in the opposite direction. So now the car is moving forward, but your friend is pushing backwards. The angle between the force your second friend applies and the displacement of the vehicle is 180 degrees. Right? Car's moving north, your friend is pushing south. Or car's moving east, your friend is pushing west. When you plug in a cosine of 180 degrees, the value is -1. What happens is your friend is doing negative work on the car. is actually taking away kinetic energy from the car, energy of motion. We'll talk about that in a moment. And then finally, your third not so bright friend gets out of the car and starts pushing on the driver's side door. So the car is moving to the east, but your friend is pushing to the north. So car moving this direction, your friend is pushing towards the camera as hard as he can, or hard as she can. Well, the angle between the displacement of the vehicle, which is moving in one direction, and the force your third not so bright friend applies, which is at 90 degrees, cosine of 90 degrees is 0. Your friend, not so bright friend, does no work on the object. And that's an important distinction. Work acquires a force being applied and the object moving, a displacement d. This bead has to move. I can stand here pushing on this dry erase board, or imagine a giant boulder. I just throw myself into it, pushing as hard as I can for as long as I can. But if that boulder does not move an inch, then I've done no work, according to physics. A force has to be applied through displacement. A force alone on an immovable object does no work. And that force has to be, the force has to be, some component of it at least, has to be in the direction of motion. So I push really, really, really hard on a car and it rolls sideways, 90 degrees from the direction I'm pushing, I do no work on that car. So that's the right-hand side of this equation, that's work. Left-hand side of this equation deals with the speed of the vehicle and the vehicle's mass. We're going to call that relationship the kinetic energy, energy of motion. So the famous kinetic energy equation is 1/2 mv squared. So that's an equation you'll be using quite a bit. 1/2 mv squared. That defines the kinetic energy of an object. And v is the object's velocity with respect to the observer. So for example, a baseball that's traveling at 100 miles an hour has more kinetic energy than a baseball traveling at 50 miles an hour. A freight train traveling at 1 mile an hour has more kinetic energy than a baseball traveling at 100 miles an hour because a freight train has far more mass. This speed is squared, but note that both work and kinetic energy are scalars, not vectors. This force is a vector, this displacement is a vector, but you're multiplying it by the angle between them. Your result is a scalar, also known as a dot product for those of you who've had the calculus and worked with vectors before. Kinetic energy is a scalar. Kinetic energy has no direction associated with it. Now both work and kinetic energy are measured in units called joules. Energy and work are measured in joules. There's a capital J to represent joules. 1 joule is equal to 1 kilogram meter squared per second squared. And you can kind of see that from this equation, like the kinetic energy equation. 1/2 the mass is in kilograms, times the speed squared. Well, the speed is meters per second, but when you square it, you get meters squared per second squared. Note that a joule is different than a newton. 1 newton, a newton of force, is 1 kilogram meter per second squared, right? A force is mass times acceleration. Acceleration is in meters per second squared. Masses are in kilograms. But work is force times displacement. Force is in newtons. Displacement is in meters. So when you multiply a kilogram meter per second squared by a meter, you get a kilogram meter squared per second squared. So units of energy are measured, SI units of energy are measured in joules. But you might be more familiar with other units of energy, like the calorie. Now, a calorie is interesting because there are actually 2 types of calorie. And if you had a chemistry class, you probably know this. There's a small C calorie, and there's a big C calorie. The big C calorie is 1,000 times bigger than the small C calorie is. Or you might have heard of erg as a unit of energy. It's an esoteric unit of energy. But the SI unit for energy is the joule.